Before we move on to the third periodic trend, let's do a few more examples with ions so we make sure we feel comfortable. So we're going to be looking at examples 4, 5, and 6. In example 4, it asks us to indicate which is larger in each of the following two sets. In each of these problems, we're looking at a neutral element compared to its ion form. So in the first problem, chromium 3 plus or chromium, which one would be larger? Remember, the cation will be smaller than its neutral counterpart, so chromium neutral will be larger. However, when we're referring to a neutral atom and its anion counterpart, the anion is always larger because of the addition of extra electrons, increasing repulsion. In the second question, example 5, it asks you to identify the largest or smallest ion from the following. Now, before I start getting into anything specific, I'm going to take note specifically of where all these ions are located on the periodic table. If I locate magnesium, nitrogen, oxygen, sodium, and carbon, I notice all of those 5 ions are all wrapping around the same noble gas, which is neon. So what does that mean when they wrap around the same noble gas? It means this is an isoelectronic series. And so knowing that will actually help me solve this problem. What do all 5 of these ions have in common? They all have the same number of electrons. They have the same electron configuration. But what do they not have in common? The number of protons, because they're all different elements. So what I'm going to do right below is I'm going to write the number of protons each of these atoms would have. Magnesium would have 12, nitrogen would have 7, oxygen would have 8, sodium would have 11, and carbon would have 6. If you remember from topic 3 videos, we talked about an isoelectronic series a little bit. Since all 5 of these ions have the same number of electrons, we don't have to worry about asking ourselves questions like, well, how many shells do they have? Because they're all going to have the same electronic structure. It's really only the nucleus that's different. So if I think about all of them having the same number of electrons, which by the way, it would be 10, but regardless, they all have the same number of electrons, but the amount of pull on those electrons are different. With regard to the first question, identifying the largest one, the largest out of all of these is going to be the one whose nucleus is the weakest, who's not able to pull in the electrons as tight. And therefore, carbon with a 4 negative charge would be the largest. The one that would be the smallest is the one whose nucleus is the strongest, and that's magnesium. If you remember, there was a little trick that I taught you. The most positive ion out of all of them that are isoelectronic is going to be the smallest. And the one who's most negative out of the isoelectronic series will be the largest. Finally, example 6. Which of these ions is the smallest? If I take a look at where all those ions are on the periodic table, potassium, strontium, iron, and sulfur, this is not an isoelectronic series. So I can't necessarily, well, at least in full it's not. So I can't use the same trick I use in example 5. But what I can do is I can notice that there's a positive, and there's a positive. How about I use my periodic trend on those 3 since they're all cations. So if I take a look at where potassium is, strontium, and iron on the periodic table, and let's figure out which one of and I'm asked to ultimately figure out which one's the smallest. So which one of those would be smaller? Well, I can get rid of strontium because strontium is in one group below. So it's going to be larger than potassium and iron. And if I compare potassium and iron to each other, the one that's going to be the smallest out of those two is iron. So I can get rid of potassium since potassium would be larger. So iron is ultimately looking like it might be the smallest, but we still need to compare it to sulfur with a -2. And to do this, we need to look at what the structure is of all the electrons. Alright, so let's do that. Alright, so on the screen, I went ahead and drew the electron configurations for iron 2+, which is going to reference argon, and then 3d6. And then I have the electron configuration for sulfur 2-, or the sulfide ion, which is going to be analogous to the argon electron configuration, which argon has 3 energy levels. Alright, so how do we use that information, right? How do we figure out which one's going to be ultimately the smallest? Well, sulfur has 16 protons at its nucleus. Iron has considerably more. It has 26 protons. And since iron has 26 protons, whereas sulfur only has 16, but both of these ions have 3 energy levels, then it would make sense that the iron one will be able to pull the electrons in tighter, ultimately resulting in being the smallest ion. Now, one thing that you may be thinking of is, but wait, iron has more electrons. If you count up how many electrons that iron has 24 electrons, whereas sulfur 2- has 18. So since iron has more electrons, wouldn't that increase the repulsion? And you are right. There does seem to be, this is kind of a challenging question. There does seem to be a little bit of, 2 reasons as to why one might be larger or smaller than the other, right? But because they both have 3 energy levels that the electrons can exist in, but the effective nuclear charge or strength of the nucleus of iron is considerably stronger, that is going to be enough to kind of overcome or dominate out of those 2 trends. So you're right, there is a little bit of, it's a gray area, and so you kind of have to reason through that a little bit. But the stronger effective nuclear charge for iron is what ultimately results in it being the smaller when compared. But like I said, that's a fairly challenging question. That's not something necessarily that you might have, it's not as easy as like example 4 or even example 5. So definitely a challenge. Hopefully, though, working up to at least getting it between these 2 elements, sulfur and iron, was easier. But then ultimately, yes, that last bit of information might have been a little tricky. Okay, so we move on to now the last 2 periodic trends. The second to last one is ionization energy. And before we can talk about the trend of ionization energy, we first need to even know what ionization energy is, because that's not something we've probably heard of before. Ionization energy is the minimum energy required to remove an electron from an element in the gas phase. Let's point out some important information that was said. First of all, it's energy required. You have to put energy in to make this happen. Secondly, what are we doing? We are removing an electron. Now, it happens to say in the gas phase, but the only reason it says that is because we need to be consistent with what we're talking about. Different states of matter react differently. So to kind of create an equal playing field so we can have a consistent definition, we just add that in. The really important parts to notice is it's the energy required to remove an electron. Now, what are we creating when we remove electrons? We're creating cations, right? We're creating positive ions. Now, since most atoms, other than hydrogen, have multiple electrons, you can do this over and over. You can remove the first electron, which is known as the first ionization energy. You can remove another electron, which is the second ionization energy, and so on and so forth. It is important to note that the first ionization energy is the easiest, and then it just keeps getting harder and harder to remove electrons. Why is that? Well, let's take a look at a really simple example. Let's take a look at a lithium atom. Okay, so we have lithium, which has 3 protons. And since lithium is in row 2, it has 2 energy levels. So let's draw those energy levels in. All right, so there they are. And since we're looking at a neutral lithium atom, so if I was looking at a neutral lithium atom, which has 3 protons, it must have 3 electrons. The first 2 are in the first energy level, and then the third electron is in the second energy level. Now, real quick, you're like, how would you know that? Remember, electron configurations tell us a lot of information, right? The electron configuration for lithium is shown here. 2 electrons are in the first energy level, and that 1 electron's in the second. So remember, you can use electron configurations to help you do these simple drawings. But nevertheless, let's talk about the idea of ionization energy. I would like to remove the first electron from lithium. In other words, this outermost electron that's out here, I'd like to remove that electron. Okay, well, that's going to take some energy because the nucleus is holding on to that electron. It's not going to necessarily give it up naturally. It's going to require a little energy to overcome. Okay, let's say, just for example, I remove that outer electron, and let's say it takes 500 kilojoules of energy to do that. I'm making up that value. I don't actually know off the top of my head right now. But let's say it's about 500 kilojoules. Okay, great. I put that 500 kilojoules in to remove it, and now I've done that. That 500 kilojoules is known as the first ionization energy. Sometimes we will denote it as I, E, and sub 1, the first ionization energy. Now, what if I wanted to remove another electron? In other words, I wanted to remove the second electron, this one right here. Well, the first one took 500 kilojoules. Do you think it would take double that, maybe 1,000? No, it's not going to take 1,000. It's going to be significantly more energy, maybe about 5,000 kilojoules. Like, whoa, why the heck does it take so much more energy to remove the second electron? Because notice where the second electron is. It's now in the energy level closer to the nucleus. Before, our first electron was out here, further away from the nucleus. It was easier to pull that away. But once I get closer to the nucleus, it now is being held tighter. Not only that, but the 3 protons were originally pulling on 3 electrons. But now, the 3 protons are pulling on 2 electrons. It's kind of like, an analogy I like to think of is kind of like when you have, kids and it's 2 parents. Let's say 2 parents had 5 kids. It's like, oh goodness, I can't. We have no control. We're losing control. But as the kids start moving out, and now the parents have the 1 kid left, it's a lot easier to make sure you have more control over the 1 kid because the other 4 have gone off to college or they've moved out or whatever it is. It's the same idea with the atom. The protons have much more control as electrons start going away. And if we take a look at that lithium example, look at that. I was pretty darn close. Notice how the first ionization energy is relatively easy, doesn't take as much energy. But once you get to that second, it's a lot. And that's because the second and third electron are closer to the nucleus. Now I'm going to jump back real quick because I want to show how we can note this. This is actually an equation we can use to denote ionization energy. Notice I have neutral sodium on the left. But after it loses an electron, and that lost electron is indicated right here, this is what would end up resulting. You have the electron that is now lost, and you're resulting in a sodium ion with a positive 1 charge. What if, and also, by the way, this represents the first ionization energy. I know that because, what did I start with? A neutral atom. So this is the result after losing the first electron. What if I saw this? What if I saw Na plus yields Na2 plus an electron? What would that indicate? Well, notice I've already started out with the ion. I've lost 1 more electron now. Now it's Na positive 2. This would be known as the second ionization energy because I notice I'm starting out with an ion already of positive 1 and now I've lost the second electron. So you can represent that in an equation. Here's the trend. We notice ionization energy increases as you go from left to right. Why is that? Because effective nuclear charge, it increases from left to right. Elements on the right hold their electrons in tighter. Therefore, it requires more energy to remove them. And we notice ionization energy increases as you move up. Why is that? Well, think about lithium, which only has its 2 energy levels, compared to, let's say, potassium, which would have 4 energy levels. Think about removing an electron out here from potassium versus removing an electron from lithium, which is in the 2nd energy level. Lithium, while it doesn't have as many protons as potassium, lithium is holding that electron in tighter than, say, the potassium, because this outer electron in potassium is being shielded by all of these electrons in here. So that electron is real easy to take out. So based on this trend, which element on the periodic table would have the highest ionization energy? Well, if we go up and over, helium would be the highest ionization energy. This just shows that it is a trend. You notice there are little anomalies in there, but for the most part, ionization energy does increase as you move from left to right. All right, we're going to end the video here, and we'll pick up with this example 7 in the next video.